Okay, really common topic, transformers. Absolutely have a go and make sure you've got this question in front of you. You may have done the question or marked it. Okay, I'm going to go through my explanation of the answers and we'll see if we can come to an agreement about how easy or difficult this question is. So in this case, you've got to describe the construction of a step-up transformer, and you may wish to draw a label diagram. If it says draw a diagram, you may wish to draw a diagram. That's their slightly sort of, what's the word here? Guarded way of saying you should draw a diagram. Okay, if you've got a space, draw one. Okay, it won't hurt. So I've drawn my diagram. I've got a primary coil, I've got a secondary coil, I've got an iron core, I've got a primary coil which is attached to an alternating power supply. I've been a bit lazy here, I should connect all these things up. Okay, so when you're doing it, make sure you use a ruler, be neat. I did this in 2 seconds. Okay, I've deliberately put in more coils on the right than on the left. Okay, that's because this is a step-up transformer. I've got 4 coils and 2. Please do not be kind of random with this drawing. Make sure that you are specific, that NS is greater than NP, really important. I then described it, attached one coil of wire to, whoops, I miswrote here, an AC power supply. Has to work with an AC power supply, it will not work with DC. Okay, I took one coil to an external circuit, wrap them both around a soft iron core, and make sure that NS is greater than NP. And again, if I was doing this in the exam, I probably would be a bit more thorough with my names here, my sort of explanation. Take your time, explain everything that you've drawn, label everything you've drawn. You might as well, this is a chance to get some marks. Now, we're told that a step-up transformer reduces the current in the electricity transmission wire from 20,000 to 500 amps. Calculate the power lost. Fantastic. P equal I squared R. That's the equation we're going to use. Now, we don't use this very often. Okay, there's another equation, P equal to IV, which is also common here, but we don't know V. Okay, so we're going to use a different equation, P equals I squared R, 500 squared times 0.6, which gives you 150,000 watts. What this says is that 150,000 watts are being lost on our wires. Now, I think this is a really good chance just to hammer this home, and this is a very common question. Why are we doing this? Well, you notice here we're going from 20,000 to 500. So this 150,000 number might seem very big. Okay, 150,000 might seem very big. However, imagine how big it would be if it was 20,000. 20,000 is 4 times bigger than 500. So that would be 4 squared bigger, that'd be 16 times bigger. The reason we step up the voltage is to step down the current and reduce the power losses. Okay, it's a very common question. Why do we step up voltages? It's to reduce current and therefore reduce power loss. Okay, now as we know, transformers only work with alternating current. What's the difference? Well, AC, we have current changing direction. DC, current passes only in one direction. Now I've written both here, it's a 1-mark question. You'd be fine with just one of those definitions, I think. Might as well write them both just to make sure. All right, then we're into a diagram of a generator. Again, there's a common one along with the motor. Okay, and we've got slip rings. Now these slip rings are the bits really important here. They look like they could be in the position of a split ring commutator, but because we're dealing with a generator, we're dealing with slip rings, I should say, not split rings. Let's have a chat about why we need them. Well, they allow the electricity to flow out. That's one thing. Okay, the slip rings are metal. And they allow electricity. They're conductors, and they allow electricity to leave the system. Now, specifically, we could just have a wire there. It could just be an extension of the wire. However, these slip rings allow our current to pass without tangling the wires, right? Without twisting the wires up. You can imagine just 2 wires connected directly. You rotate, 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 rotate. You're going to twist up your wires. It's going to become very messy very quickly. If you just have these slip rings, it allows them just to pass that electricity without twisting. And imagine the first mark people would get, second mark less so. So that's your extra little bit there, which hopefully you can take into your exam. Okay. Final one is, and again, there's a lot going on here. So we've got a coil in a generator which is rotated at constant speed. We're being asked firstly to sketch a graph of EMF against time. Again, I think some students may miss that instruction. Okay, if you see some marks underneath the graph, you almost definitely have to do some kind of sketch. In this case, we're going to sketch. I want you to pay attention to the green here, okay, because the mark scheme says to you a couple of things. One, it must be of a constant amplitude. Okay, so constant A, that's the height from the center to the top. Okay, and it must be a constant period. In this case, my period is 1, 2, 3, 4 boxes, 1, 2, 3, and I've had a fourth one there. Okay, now, why have I drawn it? Well, because I actually wanted to draw the other one as well. It says the speed of the rotation of the coil is doubled. Describe how the EMF against time graph changes. Well, we're going to double the amplitude. Okay, we're going to have a higher wave, and we're also going to double the frequency. Notice here I've got a lot more waves now. Okay, I've got essentially 3.5 waves, where I previously had 1 3/4. So I've doubled the frequency. Another way of saying double the frequency is halving the period, and that's again a totally acceptable answer here as well. So I could have said half the period as well.